All right, in the last two lessons, we've been doing a lot of calculations. We've been doing theoretical ways of looking at how much energy a reaction might have, as opposed to the practical way that we started with the unit with calorimetry. So we can do experiments to find the energy, or we can do the calculations we've been doing for the last couple lessons. Today we're going to look a little bit more at why. Why is this reaction exothermic and this reaction is endothermic? What are the properties that make the reactions what they are in terms of energy? And to understand that, we at least need to go back a little bit and look at collision reaction theory. Now, you may not have got into this really deep in your Science 10 or Chem 20, but let me just run you through this real quick. So here's a molecule of methane, so CH4, and we know that methane is combustible. It will react with oxygen. But there's a few things that have to happen for these to react. Number one, the molecules actually have to collide with each other. So if I have methane and oxygen, but they never touch, or they're never in contact with each other, they can't react. There'll be no combustion. So number one, they have to hit. Two, they have to hit with sufficient energy. And typically, that means we're talking about temperature. Remember, the higher the temperature, the faster these molecules are moving through space. So if this just lightly bumps into methane, there's probably not going to be much of a reaction. But if we can heat that reaction up, so these molecules are moving much faster, then they're going to collide with sufficient energy to cause a chemical reaction. The third thing, and we won't get too deep into this, but it's the idea that they have to hit in the right orientation. So this, I'm just making this part up, but maybe if this oxygen hits that hydrogen, maybe nothing happens. But maybe if this molecule is rotated slightly and the oxygen hits the carbon, maybe that works. Or maybe this has to be tipped slightly so that the carbon kind of is colliding with the double bond. Like I said, we won't get into that one too much, but just the idea that they have to hit hard enough, and even in the right rotation and orientation they have to hit to really make that reaction take place. Now, this is going to do some interesting things for our reaction. So first off, let's just look at the reaction we just talked about. We've got CH4 reacting with oxygen. Let's balance 2 oxygen to make CO2 and 2 H2O. So if we draw these out, remember that methane is a carbon with 4 hydrogens. I know that oxygen, I'll just draw one of them, is an O double bonded to another O. Carbon dioxide is C double bonded to 2 O's, and then I have an H2O, like that. Now, if we look at the bonds inside of this methane, these carbons bonded to hydrogens, you'll notice on the product side, those bonds don't exist anymore. There are no carbons bonded to hydrogens on the product side, which means all of these bonds have to break. Oxygen, the same thing. There's oxygen double bonded to another oxygen, but those bonds don't exist on the other side. Oxygen's not bonded to oxygen anymore. So these bonds have to break as well. Okay. Now, in your notes, you'll notice it says that breaking chemical bonds requires energy to be added. So in order to break these chemical bonds, I have an energy input. So energy has to go in order to break those chemical bonds. And that energy is probably coming from that kinetic energy from the heat that we were just talking about. The second thing in your notes is when chemical bonds are formed, energy is released. So on the product side, none of those bonds existed before. These are all new bonds, which means that coming out of here is energy being released. So in every chemical reaction, anytime that X plus Y combine to form something, there's going to be an energy input and an energy release, which means that our potential energy diagrams that we drew earlier in the semester or in this unit were actually probably oversimplified. So remember, we had energy potential, we had our reaction coordinate. And let's do this one, for example. It's an exothermic reaction, so it looks like this. But in reality, it probably doesn't look like that. It probably, take out this whole middle part here, it probably actually looks like this. Because there has to be this energy input when we break bonds. And then there's an energy output when we form new bonds. So the reason that a chemical reaction is either exothermic or endothermic is how these two fit together. If you have a little bit of input like this reaction here and a lot of output, it's exothermic. If it takes a lot of energy input to break the bonds and to make the products you only release a little bit of energy, then that one overall will be an endothermic reaction. But every chemical reaction that I can think of is always going to have an input and an output. So you're going to have this more of a curved diagram to really show what this should look like. Okay, so hopefully that kind of is making sense to you there. If we go back to these molecules, just visualize it takes energy for these to actually be broken off, to be removed. It takes energy to pull apart these oxygen bonds from each other. And then if I want to make the carbon dioxide, as I'm forming these new bonds, you can kind of hear it. I mean, it's not a perfect example, but you can hear it in the magnets here. There's a little bit of energy released as that's taking place. And obviously I'm going to need another one to make my carbon dioxide. And then these extra hydrogens would bond with the oxygen to form our water molecules. So every reaction is going to have those two things. Bonds breaking, which requires an energy input. Bonds forming, which is going to release energy out of the system. Now, what we call that is activation energy. So if we were to look at a graph, let's look at an endothermic one this time. It's going to look like this if we draw the whole thing out. So activation energy is, let's just read it out of the notes. The minimum energy required for a successful reaction to occur. Might be in the form of light or electricity, but more often than not, it's heat. So in this reaction, if we were to look at this, I tend to think of it as just like a hill. Imagine you're down here with a little wagon or something, and you want this reaction, these reactants, to become products. You want to get that wagon from there to here. Well, the only way to do that is if you can push that wagon from the bottom of the hill all the way to the top. It's not enough if you just push it up to here, which is where you want to end up, because you're only part way up the hill. That part's not going to help you. So the activation energy, I find the easiest way to think about it is from wherever you're starting to the highest point. So if I can get over that hill, then I know the reaction can go downhill on the other side and it'll go just fine. But I've got to get to the top. So we would call this the activation energy. And sometimes we abbreviate that as EA, right? Activation energy. But this would be the activation energy for the forward reaction, right? If we're moving from the reactant side to the product side. Remember that some reactions can go backwards as well. So if we were talking about starting up here at the top, and I want to get to the bottom, I don't have to put in as much energy. I'm already most of the way up. I just have to get from where I'm starting to the highest point. So in this case, that's the activation energy for the reverse reaction. So EA reverse. Okay, Now you'll notice in doing this though, we've added in this extra term of activation energy, but one thing I didn't change was the start point or the end point. They're still the same. And that distance between the start and the end point, that still represents my delta H. Right? My overall change was from here to here. Even though I went past and came back down to get there, that doesn't really matter. It just matters that I changed from here to here. Okay? So that should give you everything that you need on the first page. On the next page, and I will do this on the next video, we'll go through an example of trying to pull the numbers out of a graph like this, and then move on to how this works with things like catalysts and in other chemical reactions.